Hi, welcome back. So in this video, we're going to just introduce the differentials, dx and dy. Talk about what they mean, do a quick example. So first of all, we always start with a differentiable function. So suppose y is a function of x and it's differentiable. Then the differentials, dx and dy, are defined by this equation. dy is equal to f prime of x times dx. So notice in this equation, dy is a function of both x and dx. So x and dx are considered independent variables, and dy is the dependent variable. So let's do a quick example. Just find a differential. Given y is equal to x times e to the negative 4x, let's find the differential dy. So the function f of x is the function x times e to the negative 4x. So let's first find f prime. Using the product rule, f prime of x is the first times the derivative of the second plus the second function times the derivative of the first. Now let me simplify this. So I factored out an e to the negative 4x from both terms just to simplify. So I get e to the negative 4x times 1 minus 4x. So that's our f prime of x. So now we can just write down our differential. dy is equal to f prime times dx. And that's it. So we're going to look at now what dy represents geometrically. So we're going to look at the difference between dy, the differential, and delta y, the change in y of a function. So let's just look at a curve. Y equals f of x, some curve. And so let's take a point on that curve and draw the linearization of f of x at that point P. So remember, the linearization at a point is the same as the tangent line to the curve at that point. We call it the linearization of f of x because for points on the curve that are pretty close to P, we can get the y-coordinate on that red curve of the point. The y-coordinate we're interested in is pretty close to the green line, the tangent line. And we can use the y-coordinate on that green line to approximate the y-coordinate on that red curve. And so we call it the linearization because it's for points kind of close to P, it's pretty good approximation to the function. All right, so let's pick a point Q, also on the red curve, a little away from P. And now the x-coordinate of Q, we can just call it x plus delta x, right? And there's delta x, the difference between x and delta x. And now the delta y is the change in y. Okay, so we know what delta x and delta y are. But what are dx and dy in this picture? Well, dx is always the same as delta x because when we plot a point on the green line just above the point Q, that point R that I just drew on the green line has the same x-coordinate as the point Q. Okay, so the point on the green line just above the point on the red curve, they have the same x-coordinate. And so the dx is the same as delta x. But dy is different. So delta y is the change in y on the red curve. But dy is the change in y on the green line. So we can see here from the picture that delta y and dy are not the same. And the difference between those two y-coordinates, we call that the error. Because if we want to use the point R, the y-coordinate of the point R, to approximate the y-coordinate of the point Q, we know we're off by a little bit. And the amount that we're off by is called the error. And we can see from the picture how much it is. All right, so I'm just going to summarize. Delta y is the change in the function f of x. Dy is the change in the linearization L of x. And the absolute value of the difference, because if my tangent line were below my curve, the difference might be negative. So we take the absolute value of the difference, and we call that the error. The error when using the linearization to approximate the function. All right, so that's our basic introduction to differentials, and there'll be another video with more examples. And I'll see you in the next video.